Welcome, fellow chemists, to my final video in this brief SN2 reaction series where we will investigate their reversibility. Here are some simple SN2 reactions that can occur, but let's have a closer look at this one. It appears to be a fairly typical SN2 reaction with hydroxide as the nucleophile and chloride as the leaving group. But the reverse process also appears to be a typical nucleophilic substitution, just with chloride as the nucleophile and hydroxide as the leaving group. If this reaction could occur in both directions, we would just indicate it with a double arrow. However, there is no need for that in this case because the reverse reaction does not occur at all. In fact, it isn't just this one, but all of these reactions are proceeding in only one direction. Why? The answer lies in a comparison of the leaving groups. Since the reaction proceeds in the forward direction, we can say that chloride is a good leaving group and hydroxide is a good nucleophile. However, since this reaction does not proceed in the reverse direction, we can say that hydroxide is a bad leaving group and chloride is a bad nucleophile. Those statements apply specifically to this reaction where we already know the outcome, but how can we determine anything about a reaction if we are initially unsure? If you watched the previous video, you'll definitely remember we can identify good leaving groups solely on the strength of the acid. This is good because the book I'm reading claims most people find it easier to compare the acid strengths of the conjugate acids. I have no idea if it's true or not, but the statements on the screen are all about drawing conclusions based on acid strength, so let's stick with it. The original acid of iodide is of course hydroiodic acid. You may remember from general chemistry that this is a strong acid, meaning iodide itself is a good leaving group. This is a good case for the forward reaction, but we can't be sure until we compare the cyanide. It comes from hydrogen cyanide, which is not on the strong acid list from general chemistry. Since it is a weak acid, that means cyanide is a poor leaving group, confirming this reaction proceeds in the forward direction. So we can still use prior knowledge to determine an outcome, but there is another way to justify this conclusion using acid dissociation constants. These numbers are more commonly referred to as pKa values and are a quantitative measure of the strength, with lower values representing stronger acids. For the acids associated with this reaction, hydroiodic's pKa is -10, while the weaker hydrogen cyanide is 9.1. The difference between the two values of 19.1 helps explain why this reaction proceeds in the forward direction. Cyanide is a strong base which can push the reaction forward, but iodide is a weak base which cannot reverse the process. You could argue we didn't need pKa to determine the outcome of this reaction, but they can be very useful for other ones. The leaving group in the forward process is chloride, and its acid has a pKa of -7. You probably already remember it's a strong acid, so you might think we're headed towards the same conclusion we just made. In the reverse, the leaving group is a methanol, and its acid is not on our list of general chemistry acids. Its pKa is -2.5. With the lower pKa, you'd think that chloride should be the better leaving group, but when it comes to pKa, anything with a value less than 0 is essentially completely deprotonated, or in other words, is considered a strong acid. Having two strong acids means the conjugate bases are both weak, and therefore chloride and methanol are good leaving groups. The result is a process at equilibrium where the forward and reverse reactions are occurring simultaneously. We can still force this reaction to go in the direction we desire as long as we are clever and take advantage of one of the guiding principles of equilibrium chemistry. To demonstrate, let's consider this system at equilibrium. The bars on the left represent reactants A and B, while the two on the right are products C and D. Currently, the height of the bars for the reactants is about twice that of the products. According to Chatelier, if this system is disturbed, it will adjust to the change and establish a new equilibrium. I will disturb this equilibrium by removing half of the products. The system is now thinking, wait a minute, where did my products go? I need to make more. The equilibrium now shifts to making more products, and in an equation that might be shown by adjusting the arrows like so. In this overly simplified model, a new equilibrium is eventually established that looks similar to the original. The true amounts are different, but the ratio is the same. Now let's put the reaction back on the screen and apply the idea. The initial product after substitution is protonated. If we choose our solvent correctly, in this case using a neutral solution, the product will lose a proton forming methoxyethane. The reaction at equilibrium contained a protonated product which is now gone, so equilibrium has been disturbed and the system adjusts by making more of the protonated product again, which loses a proton forming more methoxyethane, and so it continues to make more of the protonated product, and the equilibrium continues to shift to make more and more and more until the reaction is finished. Chemists are a clever bunch and have figured out how to mess with the reaction conditions to ensure they get the desired product. But I know that all of you watching this are also a clever bunch, so let's apply what we have learned to answer the following question. A student intends to react propyl chloride with potassium iodide. In their first attempt, they picked a generic solvent and produced a roughly equal mixture of propyl chloride and propyl iodide. When they chose acetone as the solvent, the yield of propyl iodide increased. Why? Let's first start with writing our equation. On the left, chloride is of course the conjugate base of hydrochloric acid, which we know is a strong acid. Since this indicates chloride is a good leaving group, the reaction definitely goes to the right. On the other side, we find iodide, which is the conjugate base of hydroiodic acid, another strong acid. On its own, iodide can also be described as a good leaving group, and this pushes the reaction to the left. Since both ions are good leaving groups, this explains why the first attempt reached an equilibrium state with roughly equal mixes of halides. However, the second attempt, a different solvent was used, and hopefully you saw the clue pop up informing you that potassium chloride is insoluble in acetone. This means any form will precipitate out of solution, removing it from the system. The system has lost one of the products, so equilibrium shifts to make more. Potassium chloride drops out again, shifting the equilibrium further to the right. This continues until a new equilibrium state has been reached, or, as I'm showing here, the reaction finishes altogether. Like potassium chloride and acetone, it's time for me to drop out of making SN2 reaction videos. We've covered a lot, and SN1, E1, and E2 processes are in the distant future as I've got some other project in the works now. Until I post again though, thank you very much for watching.